Hello, my name is Kenton Payne. I'm an applications engineer and I'm going to present Bluetooth 5 on the CMW platform. So firstly, we're going to discuss the physical layer improvements or changes that have been made. So here we have the 1 megasymbol per second, which is the legacy mandatory rate with a frequency deviation of 250 kilohertz. We then have the optional 2 megasymbol per second rate, which increases the frequency deviation to 500 kilohertz. And we also have the optional long range, or LE coded as it's known, with S equal to 2 or S equal to 8 repetitions, which reduces the data rate down to 500 kilobits per second and 125 kilobits per second respectively, which can give you up to a 4 times improvement in range. We also have an optional stable modulation index, which has been added in for Bluetooth 5, which increases the tolerance to plus or minus 1% from what it used to be, which was plus or minus 10%. This, in theory, can give you a 3 dB improvement in the link budget. There is also the option for the 255 byte payload for advertiser packets, which is an extension. With all of these new rates that have been included, there are a lot of test cases. So in total, there are 47 test cases defined by the Bluetooth Special Interest Group. 11 of these are transmit, and 36 are receive. All of these can be measured on the CMW platform with the use of the CMW Run Sequencer tool. Now I'm going to show you some transmit and receive measurements on the CMW itself. So firstly, we come into the main signaling window. So the device under test I've got here today uses a USB to RS232 interface over HCI and 115 kilobit data rate. So first of all, we will just refresh the device, reset it, and check the RF connection is all good, which it is. So firstly, we will look at the 1 megabit per second low energy rate, and we're on channel 19 here, payload 37 bytes and alternating pattern type. So firstly, we'll go in and take some transmit measurements. So we go into the transmit multi-evaluation window. Here, we switch it on, and here you can see an overview of the measurements. We've got power versus time, frequency deviation, ACP, and some scalar measurements as well included here. So now what we'd like to do is to actually change the phi type, which we can do here. So we can change between 1, switch to 2 megabits per second, and you can see the power versus time has been reduced down to about 200 microseconds, about half, because of doubling of the data rate. We can also then switch into long range. Here we've got S equal to 2. Again, you can see the time duration increase. And again, you should see the time duration increase for S equal to 8. There you go. So all of those can be measured seamlessly here on the overview. If we just switch back to the 2 megabits per second, and we want to look at the ACP, so we can just zoom into the ACP, and to look at the ACP measurement here, we come up with plus or minus 5 channels by default. However, we can switch into the all channel mode. Here we go. So we can look across all channels, and you can see here we're transmitting on channel 19, but we're looking across the whole bands as well. So those are the transmit measurements. So if I switch those off, and we're now going to look at the receiver measurements. So if I come and go to tasks, and we select receiver measurements. So we're on 2 megabits per second, and the transmit level from the CMW is minus 86 dBm, which is a little bit above the expected sensitivity level of this device under test. And we're going to send 1,500 packets to the device, and we're going to measure the packet error rate. So we run the test. So here you go. We've managed to complete the test, and you can see here a packet error rate of 1.2%, which is within spec, so we haven't reached the sensitivity level yet. So that's just a spot check at minus 86 dBm. However, a nice function on this is you can also select PER search, which will actually find the sensitivity level for you automatically without you having to do it manually. So if we increase the start level up from minus 86, so that's already quite close to the sensitivity level. So if we say minus 80 dBm here, and we have a step size of 0.5 dB, and we're sending 200 packets this time to speed it up. So if we now come on and switch the measurement on, you can see the count here happening, and you can see the level has been reduced down to, well, in fact, it was reduced down to minus 88.5 dBm where it failed, and then it's told you the last known passing values. The sensitivity level of this device on channel 19 is minus 88 dBm. So if we now switch back to the PER tab, I'd like to show you the Dirty TX options on here as well. So we have a Dirty TX tab. So by default, Dirty TX is off, but we can enable it. And we have different modes, single value mode or spec table. So spec table, and we can show you the spec table here, is the predefined table defined by the Bluetooth Special Interest Group, and you can see the frequency offset, modulation index, and symbol timing error are all as per the spec. However, you can also select single value mode. Now, what's good about single value mode is that you get to define the range. So here you can see that the default is 0.5, but you have the option to go between 0.4 and 0.6. So in actual fact, it gives you greater flexibility than this spec. We can also adjust frequency offset. Again, we can go beyond the spec to plus or minus 250 kilohertz. We can also adjust symbol timing, which by default is off, but we can have negative 50 ppm or positive 50 ppm. And we can also define the frequency drift that used to be 625 hertz and has been recently increased to 1,250 hertz. So these are the Dirty TX parameters that are also possible to measure with. So I've shown the powerful transmit and receive capabilities of the CMW 270. Additionally, the CMW platform from Rohde & Schwarz can cover all of the test cases defined by the Bluetooth Special Interest Group. Thank you.